Hello, and welcome to the Continuing Education Center, sponsored by Digi-Key. I'm your host, Ann Thrift, Senior Technical Editor for Design News. You're eligible to earn IEEE Professional Development Hours by attending these courses and participating in the chat function. There are some important things for you to know about earning the hours. The most important ones are that you need to attend these courses live, you need to attend a minimum of 2 of them per semester, you need to fill out a course evaluation form within 2 weeks of the end of the class. You need to attend 4 out of the 5 classes per course, and you need to participate in the chat function every day that you attend. Please click on the link at the top of any of the CEC pages that says, How do I earn IEEE Professional Development Hours, to read all of these important details and more. And now I'd like to introduce you to this week's lecturer, Jacob Beningo. Jacob is a certified software development professional whose expertise is in firmware for embedded systems. He successfully completed numerous projects such as architecture design and review, bootloaders, design and implementation, software process improvement and training across multiple industries, including automotive, consumer, defense, medical, and space. This week's course, Embedded System Design Techniques, Getting Started Developing Professional Embedded Software, begins today with electrical engineers, computer scientists, and the science of selecting microcontrollers. If you haven't already, download the presentation from the classroom page. Above the live chat window, there's a heading that reads Special Educational Materials. Right-click on the link for today's slide deck, save it to your desktop, and then open it so you can follow along with Jacob. Jacob will go through his presentation, which will take about half an hour, and then he'll come on to the live chat and answer your questions directly. Jacob, now I'll hand it over to you.
All right, thanks. Well, welcome everybody to Getting Started Developing Professional Embedded Software. I'm Jacob Beningo, as I was just introduced. Thanks for coming and attending today. I think it's going to be a pretty interesting series. We're going to be talking about how we go about developing professional embedded software. Now, I work with a lot of different companies around the country and around the world, and I've seen some development efforts that don't quite fully follow the whole professional embedded software type of endeavor. A lot of functional code, a lot of development environments that aren't really set up properly. I see a lot of selecting processors kind of the wrong way, and there's some interesting things that are happening really in the industry that's kind of changing the way that we do things. So that'd be kind of interesting to do a course that kind of covers some of the fundamentals, taking a look at a little bit more high-level point of view. We're covering some really important topics that I think will help you in your embedded software development efforts. So if you take a look at slide number 2, this kind of gives us the overview of the course. Today we're going to talk about electrical engineers, computer scientists, and the science of selecting microcontrollers. And kind of what we're going to dig into today is really how do we go about selecting a microcontroller. Everybody has a different perspective on what's the right microcontroller for a particular application. Electrical engineers are going to have one point of view, a computer scientist a different one, maybe even a technician would have a completely different one. So it really is going to make a difference based on what our perspectives are, but then also just some of the new things that are coming out in the industry that I'm going to want to talk about that should influence our decision when we're selecting a microcontroller. So we're going to dive into those details today. And then tomorrow we're going to talk about the tools of the trade. We're going to talk about some of the tools that I found to be extraordinarily useful when I develop embedded software or when I analyze code as I'm getting a bench up and running and starting to test things. So we'll talk about some of those tools in detail. I'm going to try to tell a number of stories and experiences that I've had in industry to try to give you some baseline perspectives and why it is I think the way that I actually do. On Wednesday, we'll talk about managing firmware projects. We'll talk about some of the practical things I've seen, some things that work, some things that don't. Obviously, there's lots of different ways that you can manage projects. I'll just give a couple of examples and once again, really take from my experiences to try to help you along. Then on Thursday, we'll talk about creating an embedded workbench. And this is really going to be some of the things, kind of building on everything we're talking about all week. It's going to be how we go about taking our microcontrollers, take the tools that we should be using, setting up a good, project management environment, things like setting up repositories. How do we really create a good workbench that allows us to develop embedded software quickly, efficiently, robustly, and how we should set all these things up before we ever really even start writing code. A lot of people that I encounter, they're writing code, without the right tools, without the right environments. And the way it turns out is that if you actually take a look at some of the details, even going out and purchasing some tools, people can actually save quite a bit of time and effort debugging or doing other things just by setting up their workbench properly. So I'll talk about some of those different areas of a workbench, and then on Friday we'll get into some software architecture discussions, like how do we go about creating hardware abstraction layers, what are some best practices when developing embedded software. So this is going to be mostly talking about how we get up to the point where we're getting ready to start really working on a project or starting to develop code as part of a development effort. Now moving on to slide number 3, this is a slide I usually just keep at the very end of most presentations, but at any point if I don't get to a question in the chat window or you have other questions for me, this just provides you with a couple different ways you can get in contact with me. Email probably being the most efficient way to get a hold of me. And there's also some other ways on social media. For example, on LinkedIn and Twitter, every day I put out a little embedded tip for developers that follow me, things that should help you as you're developing a new perspective on some little idea involving embedded software. So if that's something that's of interest to you, that's there for you to do as well. So other than that, though, that's about as much as I'll talk about myself as this goes. We move on to slide number 4. This just gives you some background of some different courses I've done through the Digi-Key Continuing Education Center over the course of the last 3 to 4 years. I've done 4 this year. You can see here in the center, these are some of the ones that we've already covered in. Earlier this year, we talked about bootloader design for microcontrollers, how we can do rapid prototyping with MicroPython, and then also the one we just did in July was about how we can debug embedded systems. So these were using tools like tracing tools within an RTOS and some of the higher end techniques that you can use with some of the debuggers that are out there. So those are things that are of interest to you. Definitely recommend you check the archive. A lot of cool continuing education courses, even beyond just the ones that I teach that are out there. So I definitely recommend you take a look at some of the other ones out there. All right, moving on to slide number 5. What we're going to talk about today, we're going to talk about professional embedded software development. What does that actually mean? What does that look like? I am going to provide a few of my own opinions on what that actually looks like. So hopefully, they'll give you some idea. I'm not going to try not to offend anyone or anything like that, but just kind of what we'd expect to see in a traditional professional type of embedded software development. And I'm going to try to define the lines between what we consider maybe maker or hobbyist or rapid prototyping versus maybe what we consider to be the tools and the environments that a professional embedded software developer might use if they're going to go out and develop a product for the, to actually launch into the marketplace. We're going to talk about selecting microcontroller from the electrical engineer standpoint. Back early in my career, as an embedded systems engineer, I did a lot of hardware design. By my degree and things like that, I have an electrical engineering degree. So there's a certain perspective that electrical engineer brings to the table when they're developing or when they're trying to select a microcontroller. And then there's a different point of view, which is kind of the computer scientist point of view. Now, as an embedded systems engineer, I played on both sides of the fence. So I had a degree in electrical engineering, but I essentially had a minor in computer science. Took as many computer science classes as I really could fit in my schedule. So I have that same perspective as I think probably a lot of computer scientists do. So I'm going to try to show kind of the way that computer scientists think, the way electrical engineers think, and then I'm going to try to look from a high-level point of view, kind of how we can go about balancing the two viewpoints and even take into account some of the other market conditions available to us today that might make us think a little bit differently even outside that point of view, maybe even from a management standpoint. So then we'll walk through some tips, basic tips for selecting a microcontroller. I'll provide you with that basic perspective. All right, so moving on to slide number 6, professional embedded software. Now, one of the things that we really want to keep in mind is that in today's environment, there are a lot of really cool tools out there for makers, developers who maybe aren't going to develop a professional product, but do want to go and still create things. They want to design. They want to influence the world. And pretty much everything around us is driven and controlled by electronics and by software. So even if someone just wants to be able to blink some lights or, create some basic interface, or you're some artist and you want to have something that moves and is going to be controlled by a motor, it pretty much means that they probably need to know at least something about some basic software. And it's kind of come to a point where just about everybody could say that, hey, I'm a software developer. Because the truth is, people are learning how to program in elementary school. People are starting to learn how to do basic Python on Raspberry Pis, before they even get to a point where they need to choose a career direction. So understanding programming languages is becoming very fundamental and important in our society, since everything is really software-driven to some perspective. And I say that, of course, as a software developer, so I think the world revolves around software. Other people may have other opinions, but as you know, this is going to be the perspective I kind of take with this course. So we have, the ability that, just about everyone needs to have some basic understanding about software. But there's only going to be a certain percentage or a smaller quantity of us who are actually going to become professional embedded software developers. And if you're going to be a professional developer, which I'll talk about here in a bit, you're probably not going to be developing your products using things like, the Arduino software development environment. Well, that's a great environment that super simplifies things for people who don't know the low-level details, the electronics, the microcontroller, who just want to be able to turn on LEDs or be able to easily control a motor from some super high-level APIs. Those are great tools. Even for us as professional developers, maybe doing rapid prototyping, we can still get quite a bit of benefit from it, but we're probably not going to design a product around it. So professional developers, we're really looking at using professional tools that are commercially available, tools that go into the lowest levels of the microcontroller. As embedded software developers, even though we're starting to get to the point where we're being provided libraries and APIs and hardware abstraction layers and things that make our jobs easier as far as understanding the microcontroller goes, there's still going to be times when we need to dig into those lowest levels of hardware, look into the registers, look into data sheets. And in order to do that and understand what's going on, you're not going to be able to do that with tools like a Sketch in the Arduino and things of that nature. So there's a skill level difference between what an embedded software developer needs professionally and what just maybe a generic developer who's trying to do something as a hobby needs to understand. The one is a very high level, kind of abstracted view where there's a lot of black boxes and people just know the inputs and outputs. And then there's really the professional developer who has the nitty-gritty details, understands the C programming language, understands the microcontroller, each individual peripheral, the individual bits in the registers and things of that nature. So a little bit of a difference there as far as what we probably consider to be professional versus the, hobbyist type of. Now, moving on to slide number 7, once again, professional developers probably going to be extraordinarily organized. We may have, old tools available to us, but at the same time, we're probably going out and getting tools that are going to make our lives easier. We don't mind spending $500 on a debugger probe because we know that the time that's going to save us over the course of a year is going to more than provide us with a return of investment of 10x what we actually paid for that particular development tool. So whereas, if you're not a professional developer, trying to justify a $500 investment for a debugger is going to be extraordinarily difficult. We kind of look at that difference between professional and kind of the hobbyist. From that standpoint, what's the willingness to invest in the tools? What's the actual return on investment? If you're doing something every day, that really puts you kind of more in that professional category rather than kind of the mad scientist who has his lab and, is periodically getting involved. But not that we really should necessarily create those those differences. But what we're really going to try to do throughout this course is try to define that professional environment and how we build up those tools, set them up as if we're going to develop a actual product, and then carry that on through to the way we should be doing things when we're developing professional software that's going to go in a product that end users are going to use that does have to be robust, potentially reusable, and where we have to think about things like time to market, costs for developing the product, getting support, ecosystems that we're involved in, and things of that nature. So a lot of different pieces that we're going to be kind of juggling as we go throughout the course this week, and that you should be keeping in mind as a developer anyways. All right, so moving on to slide number 8. Let's take a look at some of the characteristics that we would expect a professional developer to exhibit. Some of these are just going to be generic. Some of these are going to be very focused in on what we do as embedded software developers. So first of all, usually a professional embedded software developer is going to follow a disciplined development process. This means that we have a process that we follow, such as going out and getting requirements, developing a design or an architecture. Once that's actually figured out, we go in and we implement our code, test, and then we move into a testing phase where we're going to then maybe repeat this cycle over and over and over again. We allow ourselves to be disciplined. We take notes. We make sure that we record what we're doing. We check our inputs and outputs. We follow a very disciplined process. Pressure gets put on us, and we say, okay, that's great, but I still am going to follow the right way of doing things because I know that this product's going to get into the marketplace, and we don't want to have a recall or lose business because of taking shortcuts and that type of thing. So I think one of the first key differences that we need to keep in mind for professional developers is that we try to follow a disciplined approach. We keep a calm, thoughtful demeanor as we develop our software. So, I think that's a pretty good characteristic for us. Use design patterns and architecture. So a lot of times what I find is that people who are maybe just entering the profession, coming right out of college, kind of junior engineers, they're not really following design patterns. And these could be simple things like the way in which you set up a UART to bring data in, push the input character, use an interrupt to grab the character, put it in a buffer, and then set a flag somewhere to come back later and check and see if the buffer has been full enough to decode a packet. Very simple design pattern, maybe even bootloader design patterns, things of that nature. There's these solutions already out there, and as professional developers, we try to leverage those as much as we can. And we also up front develop a software architecture, an architecture that's going to allow us to see what it is that we're building, and then we go through and actually build it once we understand what it is that we're building. So you can imagine software architecture is like a blueprint for a building for an embedded software developer. Without those diagrams that show us what it is we're building, essentially at that point all we're doing is, if we don't have that, we're rapid prototyping, or we're just kind of treating what we're doing as a hobby and not actually as a professional discipline where we have consistent inputs and can expect consistent outputs from our work products. So then one of the things that we do as well is that I think a professional embedded software developer doesn't necessarily rely exclusively on free software. So that means that there are certainly times where we're going to go and use open source software. There's lots of it out there. Some of it's very good, some of it's very bad, but we're going to use a disciplined approach to evaluate whether we should be using free software or not. We're not just going to look at the sticker price of the software and say, hey, that's free, I'm going to use it. Instead, we go and we say, okay, what's the learning curve to learn this new piece of software? Let's analyze it. Is it actually robust? Did they go through and, do they check their inputs and their outputs? Can it recover if I provide it with a improper input? So those are going to be some of the things that we want to consider if we're looking at free software, and a professional developer is going to properly evaluate that. Whereas someone who's maybe just a hobbyist is going to say, hey, I'm going to go out and get free software because I don't have any money to pay for it. This is just a hobby. Professional is going to look at it and say, okay, is it actually going to save my company money? Am I going to save time by using this free software? Or is it easier just to go out? Am I going to save time, money, budget, et cetera, by just going out and buying commercial software, maybe getting better support and helping you get the product to market quicker? Then we're going to do things like following standards like NISR C, maybe following strict C99, other industry standards that might be out there for maybe if you're in medical or automotive, safety standards, things of that nature. Professional developer is going to have some very basic industry experience, and then also is going to understand programming language fundamentals. Very, very strong fundamentals such as, hey, if I have an input to a function, I'm going to validate that input. If I'm going to output something from my function, I'm going to validate the output before I actually do it. Defining preconditions, postconditions to anything that we write, trying to develop robust code, things that aren't functional but that are actually production intent. Now, one of the questions I have for the audience, if you just take a moment to respond in the chat window, which characteristic would you say do you currently have as a strength, and which is one that maybe needs some work? If you just take a moment to respond in the chat window, I'd greatly appreciate it. In the meantime, we'll move on to slide number 9, selecting a microcontroller for electrical engineers. So what are some of the things that electrical engineers care about when they're trying to select a microcontroller? Now, when you think about it from an electrical standpoint, electrical engineer cares about hardware. He cares about the physical package size of the microcontroller. He's going to be looking at, okay, how much room do I have on my circuit board? How much solder is there going to be? Is it, if you have a BGA type component with the pins on the bottom, that's going to have some structural, some issues perhaps when you're going to develop your PCB layout, maybe the way that the solder attaches, the way it goes through reflow. Electrical engineers are going to be thinking about those types of things. They may be thinking about, hey, how many pins do I need? What type of peripherals do I need to connect to the other components that are on the board? One of the big things that they're going to be thinking about is how can I minimize cost? So an electrical engineer is going to be looking at, okay, I need to manufacture this thing. I need to find a microcontroller that isn't too expensive. I want to find one that maybe just properly balances the cost, or maybe is just as cheap as I can get for a particular product, especially if we start moving into high volumes. We don't want to be spending an extra $1 on a microcontroller when I could save $1, if I'm going to make 1 million of them. Suddenly we start talking about, some real money there. They may be concerned with heat dissipation. And I think, some energy consumption potentially, if it's a battery-operated device or a mobile device or sensor network or something, they're going to care about the energy consumption of the microcontroller as well. For the most part, though, they're just thinking from a physical standpoint of what it is that's going to go on the board and what those, physical properties actually are. Now, if we move on to slide number 10, we have kind of the perspective of the computer scientist. The computer scientist is going to share some of those same concerns. They're going to care about how many pins are available, how many peripherals are available. But one of the things that we might find is that computer scientist is going to care about the pins from a slightly different perspective. A lot of times we try to get insights into the code that we're writing, and the only way that we can do that is to set up different pins on the microcontroller and, pulse them or, maybe put LED indicators or do interesting things to try to get performance information out of the microcontroller. Now, that might mean that a computer scientist is going to want more pins available so that they can do debugging and do some optimization with the actual software they're writing. Whereas the electrical engineer is going to say, hey, you know what? I want to try to minimize my pin count, and I'm basically going to just have pins assigned to things that need to go to other chips or that are actually needed, and they're generally going to not design in those extra pins for you for a software guy, unless you actually request them to say, hey, can you leave me 4 extra pins so that I can do some performance measurements? In which case they might say, okay, they might look at a different package or do some additional trade-offs to try to get you those so that you can actually perform timing measurements on your code. Now, of course, with some modern microcontrollers, we don't necessarily need extra pins anymore. There's some cool debugging options available to us, which we actually talked about in the last Digi-Key Continuing Education Center I did. But there's one way if you're using an old 8-bit microcontroller is to try to use a couple extra pins to try to do some performance measurements. One of the other things we're going to care about is code space. So we care about how much flash space we have available, how much RAM, real-time performance, our debugging capabilities, what type of software libraries are available. Can I get drivers right from the microcontroller vendor? Do they have good third-party libraries that are already pre-integrated? What is the ecosystem like around it? If I have questions, can I hop on a forum and get a response back very quickly? Or do I need to wait 10 days for any of my requests to be answered? These are going to be things that we care about from a computer scientist standpoint, but that don't necessarily impact the electrical engineer. In fact, the electrical engineer is probably more likely to try to choose a microcontroller with a smaller flash footprint, a smaller RAM footprint, probably isn't really going to understand fully the real-time performance characteristics of the processor and the software and how they interact together. So we really have two different perspectives that when we select a microcontroller, we need to try to balance properly. So let's take a look at how we can balance that. But before we do, one of the questions I have is what additional characteristics might we care about when we're going to be viewing this from a computer scientist or electrical engineer standpoint? If you take just a moment to respond in the chat window, I greatly appreciate it. In the meantime, let's move on to slide number 11. And this is where we're going to talk about how we can actually balance this. So we really have electrical engineers on one side and their perspective, and then we have computer scientists on the other side. We need to balance this. Now, I've worked on a number of projects where, perhaps what ends up happening is the electrical engineers go out, they design a product, and they actually do all the circuit board layout, they get everything ready to go, and then they say, hey, I need some software on here to actually run this product. And then they hand it over to, some of the bad software guys who then get the boards and they say, oh my God, this is the microcontroller you selected for this particular project. There's no way that this is, ever going to work. Maybe there just isn't enough flash, maybe there's not enough RAM, maybe there's other issues related to software, just the real-time performance. Maybe it needed, something like a Cortex M4 instead we've got a Cortex M1, or maybe we got like a little 8-bit part or something like that. I've seen it actually happen, but from the standpoint of getting that right balance, as you're selecting a microcontroller now, you really need inputs from the electrical engineers and also the computer scientists, and probably even the project management to some degree. But for now, we're just going to kind of keep that little piece of the element out of the mix. So one of the questions really comes down to when we're trying to balance this out is where do the project cost and complexity really lay when we are looking at this? And the truth of the matter is we're a software-driven society now. And selecting a microcontroller simply from the viewpoint of an electrical engineer, it doesn't make sense anymore. In fact, you're probably more likely to have a more properly balanced project or selection if you went more with the viewpoint from the computer scientists or the people who are going to be developing the embedded software. So let's move on to slide 12. You can kind of see some of the things that maybe we're thinking about. The electrical engineers, we're thinking mostly MCU costs, testing tools, standards, volume. We care about how many of these things are we actually producing, versus when we look at the computer scientists, we're worried about the drivers, schedulers, frameworks, components, integration, testing, the IDEs, the compilers, the code analyzers, standards. Maybe I have to reuse this in multiple products. That's a piece I need to take into account. There's reliability of the software, security now, be able to do firmware updates, how can I get support, what if something doesn't work. There's all these other things on the computer science side that really is going to help drive how quickly and efficiently we can write the software and make it work on a product. So when we're selecting that microcontroller, we need to start thinking about some of these things. Are the drivers already provided with this particular microcontroller? If I select one vendor and it turns out that they don't provide any driver code, I now have to write all that from scratch. So maybe that's one of the things as I'm working with the electrical engineer and he's finding that microcontroller that's perfect for his electrical needs, we're also going and saying, hey, you know what? This one doesn't perfectly meet our software needs. How about this other one? And then you kind of work back and forth until you find that middle ground where you actually have a good microcontroller that fits the electrical characteristic and also provides a good ecosystem around it that provides a lot of the tools needed by the software developers to get their job done properly. So this is kind of some of the thoughts here of things that we should be thinking about as we try to balance these two different viewpoints. One of the questions I have for you as an audience, if you can take a moment to respond in the chat window, where do you think the greatest project costs are actually located at? Is it on the electrical engineering side or is it on the computer science side? So take a moment to respond in the chat window. It may depend too, depending on the product that's being developed. If it's very low volume, it's probably definitely on the computer science side. And if it's a high volume product, that's going to be in production for a long period of time, perhaps it's, really the electrical engineering side that's actually the major focus, and the computer science side just has a bigger upfront cost, but once the product gets into production, it's much lower cost. So there are different areas of the design cycle where these two different viewpoints can kind of shift from one to the other. Okay, so let's move on to slide number 13 and talk about a few different tips for selecting a microcontroller. The first is to actually perform an electrical engineering versus computer scientist cost analysis. And we need to consider that production versus the NRE costs. There's going to be certain upfront costs, the non-recurring engineering costs that we need to figure out. Where are they for the electrical engineer side to develop and select the microcontroller? What's the cost for development tools for the computer scientist? And when I'm saying computer scientists, it's mostly I'm referring to the embedded software developers. Then we also have production costs. Production costs for the computer science side is going to be maintenance of the software, reuse, fixing bugs, things of that nature. What does that look like? Production costs. Hey, what's my volume? How many of these products am I going to? How many pieces am I going to produce a year? Things of that type of nature. So we really need to balance those two different viewpoints and look at both NRE costs before we get the product and after we've actually gotten it to market. A lot of teams that I work with tend to be a little bit nearsighted. They look at just the cost right now, and then they try to look at just the bill of material costs for production, when there's really a lot more to analyze there, such as taking into account maintenance costs, bugs, fixes within the software, and things of that nature after the case. So something to keep in mind. Maybe saving 5 cents on that microcontroller that's where you're only going to build 100 of them a year. Maybe it's worth spending the extra $2 to get a much beefier microcontroller that's potentially overkill for the particular application, but that then makes life a lot easier to develop the software on. Then we have maintenance costs. I think I already mentioned resolve bugs. And then we also have, what's the cost to pay for tools and hire in processors. Try to actually balance and optimize out this whole design cycle. A lot of times we just kind of pick and choose, and we go off to the races, and we discover that our choices weren't correct. It doesn't take a whole lot of time to do an analysis. It can be a day or two, and that could potentially save tens of thousands, or depending on the project, hundreds of thousands of dollars later on down the line, just by doing a few simple analysis on where the costs actually lie. Tip number 2, on slide number 14, examine your ecosystem. I've seen a lot of people select microcontrollers without looking to see if an ecosystem actually exists around it. And what I mean by ecosystem, example code, there's a community that actually answers questions, lots of application notes that are accurate. There's access to technical support, so if you send a question into the vendor, they actually respond within 24 hours or less. And then lots of development kits around that particular part that are inexpensive, letting you know that, yes, there is a good ecosystem here, people are using this, and you can easily get your hands available on hardware to actually do testing. I've worked on a couple of projects where the electrical engineers designed the product up front, so they had the hardware ready. They selected the microcontroller. They actually never checked to see if there was an ecosystem, if it was supported. It turned out the microcontroller actually wasn't in production. It was very hard to even get microcontrollers, and there were no application notes. There was no technical support or anything. So trying to develop the software for it was pretty much, a few people in the development team out, somewhere in one room and, banging their heads against the table because they had to try to figure out everything themselves. And as we all know, of course, the delivery was 3 weeks ago, and, people were, stressed out trying to meet unrealistic deadlines with no support and things like that. So before you select that microcontroller, make sure you have a good ecosystem surrounding it. Moving on to slide number 15, make sure that you select the larger flash option. A lot of times we end up with the ability, the microcontroller vendors provide you with multiple different options for flash and RAM, and all within the same part family. Always start with a larger flash size, develop your software, and then if there's still a lot of room left in the microcontroller, you can always downgrade the microprocessor and usually keep the pin count the same to actually match. So you can adjust the price there for production a little bit. Then that way you don't actually get, you don't say, hey, I'm going to get a 32-bit part or a 16-bit part, kilobits for flash space, and discover that, oops, yeah, I actually needed 64, but now I have to go back and rework a whole bunch of boards that are in the development environment because I got chosen the wrong part and things like that. Start with a larger flash option and then work your way back. So this allows you for better application growth anyways in the field. Robust bootloader design allows you to use an RTOS. Less time spent optimizing, trying to save 2 bytes here and there. And then code and RAM are generally at a premium, especially in a resource-constrained environment. It is getting better as the cost of RAM and flash space gets less expensive, but it's still at a premium. So we need to take those types of things into consideration. Moving on to slide number 16. Tip number 4: look for platform-based solutions. I've been pretty excited. I've been playing with a lot of different platforms that are out there or that are coming out, where basically it's a microcontroller or some type of module that provides drivers, hardware abstraction layers, frameworks already that are pre-integrated that a developer can just take it and start developing their system. I think that's actually pretty cool, and it's probably the way that professional embedded software development is going. So it's kind of slightly abstracting us a little bit, but at the same time we still get we can still see into those black boxes and understand what's going on at the microcontroller level. A lot of times these are pre-built solutions that solve common challenges, so we don't have to reinvent the wheel. They help us accelerate the design cycle, and they can improve the robustness and our time to market of our software. So I think that's actually pretty cool. So we should, as developers, when we're selecting a microcontroller or a platform, we should be trying to find platform-based solutions where all the common stuff, the drivers and maybe even some basic application code is already provided to us and tested, so that we can start focusing on our actual products at the end of the day. All right, moving on to slide number 17. Tip number 5: look for modern debug interfaces. So look for things like low power monitoring, the ability to do thread tracing, exception handling, data monitoring within the microcontroller, and then other advanced tools and techniques that are available in some of the modern microcontrollers. There's really probably nowadays not much need, if you're using a modern microcontroller, to have to add extra pins to the microcontroller to be able to toggle and try to figure out what's happening inside the microcontroller. Trace tools are starting to become extraordinarily powerful, providing a lot of useful data. So try to find those types of those type of techniques or features available on your microcontrollers when you actually select them. All right, then moving on to slide number 18. This is just a reminder about some additional resources that are available for the course. Up on my website, I will post some things like links to Doxygen templates, some example code, YouTube videos that might be useful for you to review and things of that nature. So what you can do to find that is you just go to Beningo.com, then go to our blog and Developing Professional Embedded Software. That's where I'm going to put those resources for this course. And you're welcome to go there and check that out. I don't believe I've posted that yet, but I'll make sure that gets up later today. So just some extra resources to help you as you start to develop your embedded software capabilities. So at this point, I appreciate everyone's time and attention today. And I'm going to head over into the chat window to answer questions and talk with everybody. And I'll hand things back over to Ann for now. Thanks.
Well, thank you for that excellent lecture, Jacob. To our listeners, don't go away yet. Jacob will be coming on to the live chat in a minute to answer your questions directly. We also encourage you to use the hashtag DNCEC on Twitter to share and discuss what you learned in today's class. And don't forget that you'll need to fill out the course evaluation form within 2 weeks of this Friday. There's a link on all of the classroom pages that will direct you to the form, and you only need to fill it out once for the entire week's course. I'm Ann Thrift. Thank you for attending today's course, and be sure to join us all week. Now we'll go join everyone on the live chat.